A 70 kilogram ancient concrete statue lies at the bottom of the sea, 1,500 meters below the surface, and the density of concrete is 2,300 kilogram per meters cubed, and the density of seawater is 1,025 kilograms per meter cubed. So in part A, what's the normal force acting on the statue? So we're going to start by drawing a free body diagram. So I'll draw a dot to represent the statue, and then we're going to draw the forces acting on the statue. So we have the downward force of gravity, we have the upward normal force from the seafloor, and we also have an upward buoyant force, the FB. Since the statue is at rest at the bottom of the sea, we can do Newton's first law, which is the net force is equal to 0. So we can just say that the Fn plus the Fb is equal to Fg. And we want to solve this for the normal force, so just bring the Fb over to the other side. So the normal force equals Fg minus Fb. And we can plug in the equations. So the normal force is equal to the gravitational force, which is mg, this is the mass of the object, times g, minus the buoyant force, which is the density of the fluid, times the volume of the object, times g. Notice that you know everything in this equation except for the volume of the object was never given. You were given the mass of the object, and you were given the density of the object, but never given the volume. But since density is equal to mass divided by volume, you can solve for the volume, and it's mass divided by density. So the normal force is equal to mass of the object times g minus the density of the fluid times the mass of the object divided by the density of the object times g. And now we can plug all the numbers in. So the normal force is equal to 70 times 9.8 minus the density of the fluid, 1,025, times the mass of the object, which is 70, divided by the density of the object, 2,300, times 9.8, and that gives you a normal force equal to 380 newtons. So that was for part A. For part B, what force is needed to raise the statue to the surface when possible? If I draw a three-by diagram for part B, I can stop at the statue. And this time, we'll have a gravitational force, we'll have a buoyant force. It's no longer normal force on the ocean floor anymore, but there is an upward force of tension in the rope or whatever object is used to pull the statue to the surface. Since it's being pulled at a constant speed, we're still going to use Newton's first law. The net force is equal to 0. Remember, we only use the second law when there's acceleration. So that means the two upward forces, Ft plus Fb, are equal to Fg. Notice that this problem looks almost identical to what we have up here. The only difference is we've replaced the Fn with an Ft. But everything else, the buoyant force, the gravitational force, is all going to be the same, which means that when we solve for the Ft, instead of solving for the Fn, we're going to get the exact same thing over here. So we actually end up getting the same answer, that Ft is equal to 380 newtons.